Welcome to our presentation on interatomic potentials.
The objectives that are covered in this video are to explain the origins of the repulsive and attractive parts of the potential in the Leonard-Jones potential equation, to sketch an interatomic potential curve and label its key features, to describe the relationship between interatomic potential and material properties such as cohesive energy, equilibrium separation, thermal expansion, and the Young's modulus.
Starting with the Leonard-Jones potential and interatomic potential curves, the Leonard-Jones potential, but also known as the van der Waals potential, are both functions that describe how the potential of one atom changes as its distance from another atom changes. This potential is a combination of the repulsive and attractive forces exerted on each of the atoms. We can write this function, V, as a function of R, which is equal to 4 epsilon sigma over R to the power of 12 minus sigma over R to the power of 6, where the epsilon and sigmas are constants depending on which molecules we are using. The R to the minus 12 term represents the repulsive forces that are due to the Pauli exclusion principle, and the R to the minus 6 represents the attractive forces that occur due to the van der Waals forces. If we look at the diagram on the right and the green curve VR, the lowest point of potential here occurs when the atoms are about 4 angstroms apart, which is 4 times 10 to the minus 10 meters.
Both melting and boiling point of physical properties are predicted based on the interatomic forces that bind the atoms together. Consider the interaction to isolate atoms as they are getting closer from an infinite separation. A large distance interaction are negligible, but interactions grow up as they approach each other. The region of the attractive part depends on the particular type of bonding. Repulsion between atoms when they are brought close to each other is related to the Pauli principle. When two forces are balanced or equal, there is no net force, then a state of equilibrium exists. At equilibrium, two forces are equal and there is the minimum energy E naught. The minimum energy is the binding energy required to separate two atoms from their equilibrium position to infinite. When we increase temperature, which means we add energy onto the binding atoms at the bottom of the well, they will vibrate off their equilibrium position to infinite position. The more depth the well, the more stable is the molecules, so we need more energy to melt or boiling some materials.
The Young's modulus is equal to E, which is equal to sigma over epsilon, where sigma is the stress given by the force per unit area, and epsilon is the strain given by the change in length over the original length of the material. It tells us how easily a material can stretch and deform. The force is given by the gradient, so the first derivative of the interatomic potential curve. F is equal to minus dV over dr. The steeper the gradient of F of R, the larger the force required to deform the atoms from their equilibrium positions, R naught. This means a higher Young's modulus, which increases with separation linearly. Hence, we can say that E is proportional to the gradient of the force curve, Fr, at R naught, or in other words, E is proportional to the second derivative of the interatomic potential, V of R, at R naught. A strongly curved well indicates a stiff material. A flat well tells us a material that is easily deformed.
The thermal coefficient is defined as the fractional change in length divided by the temperature change. When the temperature is 0, the atoms sit at the bottom of the well with minimum potential energy. As the temperature is increased, the atoms' kinetic energy levels also increase, which causes them to vibrate more rigorously about their equilibrium positions. In an ideal well, the well would be harmonic, meaning symmetrical on both sides, and so the distance between the atoms would remain the same however hard they vibrate. But the well is anharmonic, for example, steeper on the lower end of the distance between the atoms. Hence, the average distance between the atoms increase as you increase the temperature. The thermal expansion coefficient depends on the anharmonicity of the interatomic potential. The depth of the well is a measure of bond strength. For example, when the atoms are infinitely far apart, their energy is so much lower. Here, I've set out the derivation for the well depth. First, we can substitute the equation for R0 into the equation for the interatomic potential energy. This we can obtain by finding the derivative of the potential energy with respect to R and setting that to 0. The solution to this gives us the expression for R0, which is 2 to the power of a 16th multiplied by sigma. Once this is substituted into the equation for the potential energy and simplified, we get the expression for well depth, which is negative epsilon.
Summary. In this video, we discussed in depth the key features of interatomic potential curve, including going over some derivations.
We also explored the relations between the curve and important properties of materials. Thank you for watching, and remember, you have the potential to learn this.